Hi everybody, I'm going to review today an R script, a tutorial R script that we'll be doing this week. And I'm just going to go through it very slowly and very carefully since it'll be one of the first R scripts that we look at. And I want you to not get nervous that you don't know everything that I'm doing. Instead, try to follow along and get a gross overview of what I'm doing. You might, after watching this video or while you're watching this video, open up the same script in your computer in RStudio and run the commands as I run them. Listen along to me as I'm talking through the commands and the output, and you run them at the same time. I think that would be an interesting way to use this video. The reason I'm doing this video is because this first script will give us many of the basic descriptive statistics that you should have learned in Almost 40 or Math 8. So all that basic statistics stuff that should have happened before, we'll cover a bunch of that in this and a few other videos that you can then use. So the first thing I'm going to do is share screen here, and I'm going to share my desktop, and you see I have RStudio down here. I'm a Windows user, most of you are Mac, so for you it'll look different. So I'm going to start RStudio, and there we get our normal RStudio 4 quadrants. We don't have a script here yet, so we'll open up the script that we're going to look. So I'll click here on this yellow manila folder. That's the open button, a manila folder. In case you have never used a manila folder, here's a manila folder, and you open the folder, and so that's why it's the symbol of the manila folder with the green arrow in it. And why is it called a manila folder? M-A-N-I-L-A, manila. Well, Google it and look it up. Figure out why it's called a manila folder. It might be interesting. And so we're going to click on that button. It'll bring up our file menu. I'm going to search through my file folder section. Here's econ 4142. Here's the files 42. Here's the tutorial scripts. And we're going to open up this descriptive statistics, and I'm going to go up to the top here, and there's our script. Here's our console window. Notice way down here that I have the little side arrow, the greater than sign. So that's my command prompt. I'm rarely going to use that. Mostly I'll be in my script window. Here we have the environment window, and over here we have a set of windows, and will almost always be on the plots window. So here's our script, and the lines in our script that have these hashtags in them are just comments, and also little graphics to make the script easier to read by setting off this part as a title. We usually try and have a header in every script that gives relevant information about what the script is doing. Our very first command in almost all scripts is a command that will clear the working space that's in this environment. So let's put a few things in this environment. So I could create an object called variable x, and we'll say that it's equal to c, which means it's a vector, 1, 2, 5, 4, 58, 89. And notice how R automatically put the closed parenthesis here. And if I run that, now I have that vector, 6 numbers, an ordered set of 6 numbers here in my environment. When I click on this command, I don't have to highlight the command to run it. I can just click my cursor anywhere in the line, and then I go up here and click run, and you see that it cleared it. So I'll do that again. I click anywhere here in this cursor. I can highlight this command and run it, right? Then I can just click down here and clear the working space. Another way I can do it in Windows is I can hit command return, control return, In a Mac, you'd probably hit Command Return or Command Enter. So the cursor's there. From my keyboard, I can run it, Command Return, run the next one. It just skips over the hashtagged command. So that's how we run a command in R. So I'm going to delete this now since we've already seen what we can do there. I'm not going to talk today about setting the working directory. It's going to be an important thing. A lot of people have trouble with it. You should read the guide to R. We're just going to move on. In this tutorial script, we have a bunch of packages that I've already installed. You will have to install them, and I'll show you how to do that in class. But I'm going to run the library commands here to load these packages, and you can see I got a bunch of messages. There's some warning messages. The warning messages are not in red because anything's wrong. They're just in red to get your attention, and they're just saying, hey, you know, this package was built under this current version of R 4.0.3. I can find out what version I have by typing version down here in the console and then hitting return. And I see that I have 4.0.2. So I need to update my R to be the latest version. So I've loaded my packages. I'll continue going down the script. I have a command that's going to limit scientific notation so that I don't have, you know, e to the 10. Instead, I'll have decimal places. And then I'm going to read this California data set in. So first, I'm going to create an object called URL. So notice when I run this, now in my environment window, I have URL is equal to this website address. And then I use the command read data 13, and what am I reading into are this URL, which is the website for where this data set is stored, and I'm going to call that California schooling. So this is the assignment operator. So I run that. Whoops, I only highlighted this part. I didn't have the whole command. So I run that, and it takes a second, goes to the internet, comes back. California schools data set with 420 observations of 18 variables. I can click on this little blue button called the blue expando button, and it gives me a little brief aperçu, a little snapshot of the data and the variable names, what kind. So there's numeric variables, character variables, and I guess they're all. I will never worry about these things. So I have something called the district code, which is presumably the code for the district. It's a numeric variable, and it's a set of numbers. Then I have the county, Alameda County, Butte County, whatever, Sunol, Glen Unified School District, et cetera, right? So that's my data set. If I click here on the data, it opens in the form of a spreadsheet, and we can see our typical way our data is stored is as structured as a kind of spreadsheet. The row is the unit of observation. So each row here is a school district. The columns are the variables. So each school district is a row, columns are variables. So of course the column county and district identifies the school district and the county that it's in, and there's an ID for that. And then we have a bunch of other variables about the percent eligible for reduced meals, the percent eligible for CalWorks, the number of teachers. Maybe this is teachers in the school district. I guess 303. Let's click here and we can sort this. We'll sort it for the high, and we have Bakersfield Elementary School District has 1,429 teachers. San Diego Chula Vista has 1,051 teachers. Yeah, so that must be the number of teachers. There's a file in your thing that has what all these variables mean. So I'm going to close this. I try not to keep my tabs all cluttered here. Try and keep things neat. So once I'm finished doing something, it's better to close it. Otherwise, you tend to start getting confused if you have too many tabs open, so it's good practice. Notice that the name of my file here switched to red from black. That's because I changed it. I don't want to save this file, however, the changes that I've made, so I'm not going to save it. If I did, I could save it with this save button here. This is a representation of an old disk, a diskette, where people used to store data. You've probably seen them in your parents' homes. It was the old-time way of storing things before the cloud came along and we stored things on Google Drive and OneDrive and other places. Before that, of course, we stored things on flash drives, and before that, we stored things on diskettes or external hard drives. So the icon here, you see it up here again, is the save button. So you don't have to go up here and say file save or save as. You can just click on the button and that'll save the current document. So we read the data set in. It's called California Schools. The very first thing we're going to do here is create a new variable called small class. It's going to be a logical variable taking on values true or false. If we look over here, we can see small class, logical, true or false. If the student-teacher ratio is less than 20. We're also going to read in some data from the World Bank. So the first thing I do is I create a list of the variables that I want from the World Bank. And I know what the names of the variables are. You don't. At some point, I'll show you how to find variables from the World Bank's data set. So I click on Run. Now I have the list here. It's 10 variables. And then I use a function called WDI, which is written as part of a package called the WDI package. And we're going to get all the countries, these indicators for 1990. So I run this. And it takes a little while because it's going to the internet, to the World Bank servers in Washington, presumably, or somewhere, and calling the data, and it'll bring that data then over to me. And there it is. I called this data set WDIM, and we see WDIM is here, 264 observations of 20 variables. So it included the 10 variables I called it, and then because I said extra equals true, it included 10 other variables. And those other variables are the, you can see down here, the capital city, the longitude, latitude, and a variable that I'm going to use called region in order to sort the countries into regions. And I'm going to rename these variables, which are obviously not very intuitive. This is real GDP per capita, population, the percent of the population that's female, the percent of the population that's urban, the sex ratio at birth, life expectancy for females, for males, infant mortality rate, and the fertility rate. So if I click on this and run that set of commands, now if I look at WDIM, I see that the names have all been changed. So that's nice. These are easier to work with. I can also, if I want to, create a subset of this data set by taking out the ones that are aggregates that aren't countries. So if the region is what the World Bank calls aggregates, I'm going to take them out. That is, I'm going to use the not sign here. The exclamation point is the logical sign for not. So when I run this, you see it switched to 216 observations from 264. So 50 of those observations were aggregates, regional aggregates. Third data set we're going to read is a data set from the current population survey. So it's a data set about individuals and their earnings. So I click on that and it's going to the Stock and Watson website, and we have 15,393 observations of just 3 variables, and just have the earnings, average hourly earnings, the year, and the sex. and the gender. So that's going to be a 1 or 2. I don't know whether 1 is male or 2 is male or 2 is female or 2 is male, right? So I'm going to have to figure that out. I could look at the code book and see, but probably it'd be easy to figure out because we know, right, in general that women earn about 80% of what men earn on average without controlling for any other variables. And so all I have to do is look at the table of means by this variable, and then I'll be able to know whether the 1 is male or the 2 is female. So that's how I've read in the data set. And now we're going to calculate the descriptive statistics. We're going to use a program called Stargazer to do that. So we'll do it first for the California schools data set. We run the Stargazer of the California Schools District, and we get a table down here. And notice what the table tells us. It tells us the number of observations for each variable, the number of non-missing observations, the mean, the standard deviation, the minimum, the 25th percentile, the median, the 75th percentile, and the max value for that variable. Some of these variables are meaningful, others aren't. So if we look at student-teacher ratio in particular, which we'll be looking at a lot, we see that the average, the mean for the 420 observations is 19.64, so about 20. So 20 students per teacher, sounds about right. The standard deviation is 1.89. Remember what the standard deviation is. It's a measure of the spread or dispersion of the values of the variable. So if I look at the California schools and look at the student-teacher ratio, which is right here, right? I have 17.8, 21.5, 18.6, 17.3. So I have 420 values for this. So the standard deviation is the square root of the variance and is a measure of the spread or dispersion of this variable. So we see that the standard deviation is about 2. So the mean is about 20 and the standard deviation is about 2. The minimum value is 14, the 25th percentile, that is if I ranked all these student-teacher ratios from lowest to highest, the 25th percentile one would be about almost 19. The median is 19.7. The 75th percentile is 20.8. You can see that they're all tightly concentrated right around 20. And that's because by law, right? At the time these schools were functioning, the student-teacher ratio by the Secretary of Education in the state of California was supposed to be 20. So very few schools had class sizes greater than 20. And we see indeed that the max for any school district of the student-teacher ratio was 25.8. So these are all our, what we'd call our summary statistics or our descriptive statistics. I'm going to pause here and continue in another video so that they're a little shorter, right? You can take a break.